All right. So today, like the title suggests, I'm going to giving a walkthrough of geotechnical fieldwork in the Canadian Arctic and what that looks like in practice. So presentation overview, just real brief. We'll talk about something that's maybe absent, it's not absent's the right word, but not always discussed in technical talks, and that's the administrative side of things, preparation, safety, the importance of local knowledge. I'll introduce some resources, just documents that I've found myself going back to over and over again. And then I'll get into sort of a crash course, call it Permafrost 101. So everyone's speaking the same language. We're starting from the same from the same line, and then use that as a springboard to jump into uh, investigations and then some case studies. So without further ado, let's get started. Um, so real great scenery, Northern Canada, right? That's one of the benefits of going up there. But one of the drawbacks is you don't have access to Canadian Tire or Home Depot, right? Your drillers can't go to their shop and pick up an extra set of hollow stem augers or some fittings or hoses or whatever they need. So there's an old British military adage called the six P's. Does anyone know what that stands for? Silence, silence. Good. Okay. Proper preparation prevents piss poor performance. So it's a good thing to just say in passing, but what does that mean in practice? It means that you have a list and you're double checking it, right? I'm sure everybody does this when they're doing their geotech investigations in southern locales, but when you're in a remote setting and you don't have the ability to get extra gear, double checking that list is super important. It means you're packing your bag and then you're waiting a day, you're taking it out to your garage, you're unpacking everything again, checking that list. You're discussing it with your peers, you're discussing it with your project manager and making sure everything's there. Um, it means you're calling your suppliers, right? Have they ordered food? Are charters on time? Are the wildlife monitors set up and good to go? It means all your field staff has first aid safety training, and not just like the general level first aid safety training. They've got wilderness first aid training, right? Um, more often than not, it's you, it's the helicopter pilot, and a wildlife monitor, and that's it, right? So really, you don't have a lot of options if things go bad. Uh, you've got to be able to be comfortable in uncomfortable situations. It means developing a good rapport with the locals that you have helping you, whether that's your wildlife monitor or labor assistants. Um, it's making sure that your wildlife monitors are showing up with the right equipment, right? You don't want someone showing up with a 270 or buckshot in their shotgun that's going to just really make a polar bear angry. You are in bear country. Here's some evidence to support that. So it means you're firing test rounds when you get to site and confirming that the guns are in working condition, that they have the right ammunition. It means that you've got backup power for your polar bear fences. It's double checking your equipment, like if you have a Garmin InReach, that you're not just turning it on to make sure it works. It's your texting your loved ones with it and making sure that they text you back. So you can communicate. If you're using Starlink, it's I know how to turn it on and know how to set it up quickly if there's an emergency, and I have redundant power sources for that. Um, and again, I'll just underscore the importance of trusting your locals. Like it really comes down to this. This is land that they've been on for eons, right? They know how to traverse it. They know how to attract wildlife. And if there is an incident with wildlife, you really have only one source of protection, and that's your wildlife monitors. We've got a funny saying it. Um, it I don't know if it's funny, but when you're talking about bear safety, and if it's If it's brown, lay down. If it's black, fight back. If it's white, good night. So when you're in the far Arctic, really, like if there's a polar bear encounter, you don't have a lot of options. And last but not least, bring your fishing gear. Some of the most rewarding experiences I've had with locals up in the Arctic have been sharing stories and fishing, and sitting down and sharing a meal. So with that out of the way, these are some of the resources I consistently find myself going back to. It's by no means an exhaustive list of things you need to be a geotechnical engineer in the Arctic, but certainly a good start. These are documents that you should read, understand, and know well. So won't go through one by one, but the two things I will underscore is always pull papers, right? Educate yourself. So if you're doing a job on, say, adfreeze piles or thermosiphons, or a landfill facility that's using permafrost aggregation as a means of containment, like there's lots of good literature out there. Educate yourself. And the last is this work really shouldn't be done without the guidance of really good mentorship and experience. It's just irreplaceable, and especially when we're talking permafrost, it's required. All right, so what is permafrost? What you see here are two maps, and again, the reference in the last slide. On the left is the permafrost map of Canada. On the right is essentially the same map, showing ground ice. They show more or less the same thing. So these illustrate the distribution of permafrost in Canada. They're a little bit old. I think it's 1995 is the reference date. So certainly these lines has moved, but it's a great starting point. To get into the concept of permafrost, I think there's a little bit of a misconception, especially maybe in the non-engineering field, that it means ice. And that's not the case. It's really just a thermal condition. And that condition is that, the ground or rock is below 0 degrees Celsius for 2 consecutive seasons, right? So to kind of put that in a risk framework from geotechnical engineering, if we have bedrock that meets that condition, if there's thaw, there's probably not a lot of risk. On the flip side, if we have, say, like a silty sand and it's ice rich and there's thaw, there's a lot of risk. So again, permafrost just refers to a thermal condition, not necessarily ground ice. I'll be using a lot of words that we'll try to get into the concepts and definitions of throughout the talk, and ground ice is certainly one of them. So unpacking these maps a little bit further. On the left, the different colors represent sort of the zones of permafrost. We go far in the south to the isolated zones. So it's discontinuous both, right, with like horizontally and vertically. And the further north you go, you get into extensive discontinuous and then your continuous zones, where you have permafrost everywhere. From an engineering point of view, those zones kind of represent different risks, in the sense when you're in discontinuous permafrost, it's almost a little bit more difficult because you might have some here and you might not have some over there. That's not to not to say the risk isn't any less or any greater, because what really drives the performance is the presence of ground ice. So if you have ice-rich soils in a discontinuous zone and ice-rich soils in a continuous zone, but not over here, the risk for differential settlement is still high. The reason I wanted to start with these maps is because when I get a request for an RFP or whatever, however the work is coming through, this is generally where I start. Is where am I? What can I expect, very broadly speaking, from a permafrost condition? After that, the next best source of information is reports that your own firm or organization might have, that has testable information. It's got information on ground ice. It's got information on ground temperature, on salinity. Often in remote communities, This information isn't publicly available. Maybe your client has some. Maybe you've been able to get lucky and find someone, just from a Google search. But ideally, you've got your own information, in-house in that community or location. If not, geological maps. It gives us a very broad understanding of what the soil conditions can be, and helps you decide what you need to do from a geotechnical investigation point of view. So, am I on superficial bedrock? Great. It's kind of like our get out jail free card, as far as we can design like we would in a southern locale versus, say, we have something like a glacial marine sediments like silts and sands. Lots of potential for having ice, likely saline, which really affects performance. Again, not getting too technical. So, in a very crude manner, from performance point of view, warm, ice-rich permafrost that is saline is bad. Cold, ice-free permafrost with no salinity is good. So, with that, introduce a couple more concepts, what we call ice-rich soils, ice-poor soils, thaw-stable and thaw-unstable soils. So think of it as, if we have ground ice and it thaws, we lose all that volume, and that's usually reflected in surface settlement, right? So that's what we'd call ice-rich, thaw-unstable, versus thaw-stable. So that could be, like I've mentioned, bedrock a couple times already, but it could be a really dense till with really low moisture contents, right? So think like a dry sand. If it thaws, there's no water to really affect anything. Google Earth, always a great spot to look, especially since now we've probably got 20 odd years of relatively high quality aerial photos available. So this is just a screenshot from up in Tuktoyaktuk. And you can see right in the middle, we have some ice wedge polygons that have thawed, and, our ice wedge ponds now. So if you're pulling information and doing a little bit of a background review as part of your work, and you see this along, say, in a proposed road alignment or building, alarm bells, right? Okay, this is going to be bad ground to build on. Can we look at, relocating the site, or what are we going to have to do? It's probably going to be expensive. Just a picture's worth 1,000 words. So this is a job we did up in northern Manitoba. On the upper left, you can see a little chunk there. That's ice, about an inch thick. So that's what we'd call, ice rich. On the right, we have a dense till, same test hole, but lower down, is a dense soil that we'd call a thaw stable. Temperature profiles with depth. Extremely important for a lot of the work that we do. I'll dive into trumpet curves a little bit later. So letting the cat out of the bag a little bit there. But unpacking this a bit, x-axis, you got temperature, y-axis, you got depth. So it's just temperature with depth. On the right-hand side, you have your max. On the left, you have your min, and in the middle, you have an average. So what I wanted to point out from this is what we call the active layer. So that's the depth of seasonal thaw. Basically, the depth of your active layer is equal to the top of your permafrost. And that's where your maximum crosses your 0-degree isotherm. Other two concepts, mean annual ground temperature. So that's just the average temperature at whatever, specific depth you're looking at. And warm permafrost versus cold permafrost. So warm permafrost is 0 to -2 degrees, and anything less than -2 we call cold. Great. So we've got ice in the ground. We've got frozen ground. Why is that important? Why do we care? Right? I had to show, it's obviously not my picture, but had to show that this is a iconic building up in Dawson City. If anyone ever has the opportunity to go there, it's a really fun little town. Take that opportunity. But I think they call it the Kissing Buildings. You can imagine 100 years ago, or whenever these were constructed, probably weren't thinking permafrost, but how excited your insurer might be if you had geotechnical recommendations for a building and that did this. So that dovetails into the other three pictures, right? So this is a job that we did some support on, some remedial foundations up in the Central Arctic. And you can see some cracking in the drywall. It was grade supported. Beams are cracking. You can see all the jimmy rigging they had to do to try to just maintain this building in a serviceable state. It can certainly get a lot worse than just a little bit of cracking in the drywall. Here's a video again. This is sort of central Arctic. Let's see if the video plays. Oh, won't wanna. Well, yeah, won't play the whole thing, but um, the video underscores like the importance of good building practices, and our basements and some pits in the Arctic a good idea? Um, they're not. Uh, this next picture brought up this again is northern Manitoba that one of our folks took along a rail line. You can see how it's really up and down. That might not necessarily be all from permafrost degradation. It could be some frost heave. So which almost makes it worse because you have up and down. Any lineal infrastructure, right? Rails, roads, power lines, pipelines. Not very amenable to differential movements. So it's certainly important we consider permafrost. Um, this is another job, Eastern Arctic. We're providing some support on where we have ice-rich ground. It's thawing, producing some retrogressive thaw slumps. So that's as the ice melts, the slope just kind of lets go, and that's like further translating into some thermokarst lakes. And the issue is here, you can see on the left-hand side of the right photo that it has the potential to infringe on a runway. Obviously, planes need flat ground to land, so that's not good. All right. So we've got an idea of what permafrost is, its engineering significance. So I'd like to get into some terminology, key concepts, and some classifications. So a shout out to my friends at the Canadian Permafrost Association, great organization. Suggest you join. It's cheap. It's like $100. And if you do, you get access to this wonderful document called an Illustrated Permafrost Dictionary. The glossary is also pretty nice. And I thought this would be a good opportunity to show some photos. They're not all from the dictionary, but show some photos and do a little bit of a pop quiz. So Leo said I had some interactive portions of this presentation. So let's see what we get. Does anybody know what this is called? I know most of you do, so just spit it out. Robin Sturkey, you're on the call. You know what this is. Maybe people can't talk. I'm gonna assume that. So trumpet curve. So this is something that we want to produce if ground temperature is really key, critical to our design, which it almost always is when we're talking permafrost, right? So again, unpacking a little bit, we've got ground temperature with depth. We've got our mean in the middle, maximum on the right, where that crosses the 0-degree isotherm is the top of our permafrost, minimum on the left, what we call our zero annual amplitude, which I believe is where the temperature differential is less than 1/10 of a degree over 2 seasons, something like that. We've got our base of our permafrost, which depending on where you are in the world, like in discontinuous permafrost, a lot of times you'll find unfrozen ground underneath where you found frozen permafrost. But the further north you get, often that permafrost base is below what we'd consider significant from an engineering point of view. When we're talking foundations, maybe from a numerical modeling point of view, you could argue that you need temperatures deeper. Leo, can you hear me all right? Can you give me a thumbs up or?
Yes, we can hear you fine. I just
Okay.
allowed the chat and normally them not to unmute, but now participants have been able to unmute themselves in chat.
Okay, good. I'm imagining everyone in the background being super frustrated with all the clever answers they've been screaming out throughout this presentation. But let's see. Okay, next one. Anybody? I'll just keep going. Beaded stream. So you see these larger water bodies along these small stream or creek. So that's as water flows, it's hitting ice-rich permafrost, causing some thaw, making these larger water bodies. And again, why that's significant from an engineering point of view is if you see this along, say, like a bridge crossing, you're likely going to have some issues. Anybody? I'll just keep drunken forest. So you see these leaning trees, and it's not necessarily an indication of permafrost, but it's an indication of frost action. So whether you have seasonal frost lensing, growing and pushing these trees up, and then as it thaws, you get you get some settlement and some tilting, or it's degradation of permafrost. Could be either. Here we have called pattern ground that can manifest itself a few different ways. You can have frost sorting, frost bulbs, solid fluxion. And again, it's not an indication necessarily of permafrost, but it's an indication of frost action. Here's a photo that Robin took up in central Northwest Territories from out her plane window. So this is a good one. I like to refer to it often. So you see all these, the patterns in the ground that are, more or less right angles. Those are those ice wedge polygons that we saw earlier in the Google Earth image. So it's literally a wedge of ice in the ground. So you can imagine how much problem that might cause for any sort of civil infrastructure if that ice thaws. Again, up in the territories, so a borough area that was developed and then, you could argue not necessarily closed off properly, and you have retrogressive thaw slumps going back towards that lake. The issue here is that lake's actually higher than the lake in the background. So if that makes it all the way back, you can imagine if that water starts flowing, what's going to happen. Flowing water is like kryptonite to permafrost. It just degrades it super quick. So any ice-rich permafrost along that alignment is going to get further degraded, and then it's really just, like a snowball rolling down the hill. Permafrost classification. So, pretty old document made in the 1960s. I guess they did pretty good work back then because it's still what we use today. I won't do an exhaustive review, but real quick so everybody understands what I'm talking about. Really, really simple. We have N for non-visible, V for visible, ice for ice. So once you've identified you're in frozen soil, you visually inspect and you look for the presence of ice. If you can't see any, it's an N. And then that's further delineated into NF, so non-visible friable. Think if you took a dry soil, put it in the freezer, took it out, there's not enough moisture in there to really have it stick together, right? Then there's NB, so non-visible but bonded. You still can't see the ice, but there's enough moisture in there to hold that sample intact. And then that's further delineated into NBN, which is non-visible, bonded, no excess. So there's no free water. Then NVE, non-visible, bonded, excess. So that means there's actually free water. And how we determine that is dead simple. Just take a sample of your frozen soil, put it in a jar, throw it on the hood of the truck, or the dashboard of the truck, whatever, in front of a frost fighter, bring it to your hotel room at the night, and see if you have any free water after. And then if you do, NBE. And that's obviously important from a thaw settlement point of view. Always good to, take your pitcher with a tape measure beside it so you have a scale for how much, supernatant water you might have in that sample. Helps us to estimate the degree of settlement that we might see. V for visible, VX, VC, VR, VS, depending on the orientation of the ice. And then we have ice. So that's if it's thicker than an inch, you just call that layer ice. Again, same examples, pictures I showed before in northern Manitoba. So we'd call this an NBN. So there's no visible ice, it's bonded, and there's no excess. So you throw it in the jar, nothing comes up. Versus a VS, so this is a visible layer. Same borehole, just a little bit higher up in the stratigraphy. And again, same borehole, but we'd actually call this a layer of ice. You see, it's about 3 inches. So. All right. So we know what permafrost is. We understand its significance. We're all good on terminology and our key concepts. Someone's asked us to go up and do an investigation for, a new hotel or, for some mining infrastructure or something. So, okay, what are we going to do? This is a really good background document to start you off with um, your options. What it really comes down to is professional judgment in respect that are your investigation methods available to you in this location is suitable to assess the risk that is acceptable to your client, right? And so that's a conversation you have to have with them at the get-go, right? If they're building, I'm not saying this is happening, but the federal government has announced like 40 billion of spending in the Canadian Arctic in the next however many years. So, you know, if they're planning on building a small nuclear plant or something, but your only option is an excavator. Probably not a good idea, right? You're mobilizing a drill rig to that community no matter what. So good background document to start. Read it, and the CSA provides minimize this. Some framework for assessing that risk based on soil type, ground temperature, and where you are in the world, and then what level of some geotechnical rigor is required, whether it's qualitative, semi-qualitative, or full-on quantitative with numerical modeling and all that sort of stuff. So come on, go on here. There we go. All right. So sort of bounding it from call it best to worst, or best information to least accurate amount of information. Ideally, you can have access to roadways, or there's already drilling equipment in the community where you can get full core, full from surface all the way to the depth that you're interested to, just full core. You can imagine the heat that's generated by steel augers turning in soil. So even better than full core is full core with a circulating brine solution. So something that's -5, -4. That can keep your permafrost sample intact. Super important when you're talking critical infrastructure. So this is a job central Yukon, mobilized SEER drilling out of Winnipeg. So shout out to some local folks where it's more of a mining setup, but full core, chilled brine. Thanks to Jay Sean for the picture. I think he's on the call. Another job up here. So northern Manitoba, where we still have access to conventional drilling rigs. No, we didn't have a setup for a chilled brine, so what we ended up doing here is just pounding spoons, so SBTs. Some of the drawbacks there is, if you're pounding a spoon every 5 feet, you're only getting 30% of your stratigraphy. So do you pound a spoon twice every 5 feet to get 60, or do you pound continuous, right? And that really gives you, the more you do, the more it's going to cost. So you have to keep that in mind. And there's also some seasonality, right? Like for those of you that have pounded split spoons before, which I assume is most, if you're doing this in July and you're putting a piece of steel that's 30 degrees down the ground and trying to assess warm permafrost, by the time you get it up out of the hole, it has anything that you might interpret as ice already thawed, and you might misinterpret that, have some false positives for wet sand or something. Other options here is CRREL barrels, which is like a hollow stem barrel that produces a continuous core. Here, I've got a video of an air track rig. So that's an option in a lot of communities, specifically in Nunavut. Watch your ears, might get a little loud. Got another video later that's a little bit more dramatic, but you can see how there's a lot of disturbance in the sample. So you don't get a great resolution of your stratigraphy. You can still ballpark it. You can still see ice in your sample, which is good. Advantages to this method are you still get information with depth, right? So it's great that these rigs are in the community. It's relatively quick. It's the same equipment that is likely installing your foundation, so it's a really good interpretation of ground conditions. And you can install thermistors. Can't remember if I said that already. Probably on the towards the less useful end of things is excavators, because digging through frozen ground is hard. right? Especially if it's, really frozen clay, right? It's good luck. Maybe they've got a frost ripper, but then you're switching between your frost ripper and your tooth bucket, which takes a lot of time. Generally, where I look at excavators and say it's appropriate is if your depth to thaw stable soil is within the active layer. So if I've got, say like a dense till with no ice or a bedrock at 6 meters, but my active layer is 2 meters, no bueno. But if my active layer is 2 meters and I think my bedrock's relatively shallow and I just need to prove it out, then excavator is a great option. Locally available, relatively cheap. You can get local engagement, throw some bucks into the community. And then hand test bits. You're super limited to basically once you hit that frozen ground, you're done. You can chip away at it, but it's really hard and not fun. Lots of poor language came out of digging this test hole. Last method that I actually don't have any photos for because I've never done it, but I've attended some really good presentations from the CPA, and I read some papers about it, is the use of GPR. So a lot of development's been made in that lately. Really excited to see where it goes. And I'm sure everyone on this call can imagine the benefits of a continuous profile of permafrost along whatever you're looking at it, especially if your lineal infrastructure like a road or a rail or a pipeline. Am I doing for time? 2:35. Looking at some tools of the trade quick. This is we call it Fluke because it's the manufacturer's name, but the digital thermometer just to assess or get soil sample temperatures. Again, not a great measurement because it's a disturbed sample. It's a spot in time. By the time you get it up out of the ground and actually, put the lead into the soil, which is also difficult because it's frozen, you don't get a great reading. If ground temperature is critical to our design, which it always is, we're putting in thermistors. The one thing I'll add, caution is always calibrate. Calibrate before you go. Calibrate every day while you're on site. It's really easy to do. You're probably somewhere cold, so throw some ice in a cup and make sure it's, your instrumentation's throwing straight dice. Like I said, if things or if temperature, ground temperature is critical, which it almost always is, we're installing thermistors. So that's just a string of vibrating wires and a protective casing attached to either switch box or data logger. So I can't remember where this site is, but I recognize that switch box, so I know it's ours. Again, this just gives you a reading in time. If you're sending someone, a couple times a year, you just get those spot measurements. So if you want really good data, you install data loggers. This is, again, a site in Central or West Arctic. I can't remember where this one was. But you can set these things to read every 2 seconds if you want. I think we usually set them to about every 6 hours, just to see what daily fluctuations are doing to surfacial ground temperature. Jeweler's lens, a small magnifying glass, just to help you address or assess any invisible ice in soil samples. And salinity, for those of you that have had the pleasure of trying to squeeze the water out of this thing. It's not fun, but salinity is super important. It affects the strength, deformation characteristics of the ground ice. So when you're thinking at-freeze piles, when you're thinking any sort of surface supported infrastructure, salinity is something that you got to look into. All right, so we've gone through what permafrost is, the engineering significance, terminology concepts, the investigative methods. Our clients reached out to us and we've got an idea of what we're building and where it is. So what are our foundation options? The CSA document it's a great just decision tree on what might be viable options. And I've seen it in different formats and different documents, but this one was front of mind. So permafrost, no. Conventional southern foundation. Permafrost, yes. Do we have shallow bedrock? Again, like I said, it's our get out of jail free card. It's really the risk of thaw settlement causing issues to our structure if we're on shallow bedrock is really low, right? There's still the chance that we have, ice-filled joints and whatever in our bedrock, but they'd have to be so perfectly aligned in each of your foundation units to cause an issue. So usually shallow bedrock, we're pretty happy. Is bedrock less than 8 meters? I've been told that's maybe more like 10, depending on where you are. So 8 to 10 meters is, a good ballpark. And then you're going rock socketed pipe. Again, that removes a lot of your risk because you're founding your building on rock. If you have any surface supported infrastructure adjacent to it, right, you have to account for the differential movement. So you think, like utilities, approach slabs, things like that. Do we have to worry about down drag on our piles if there's thaw? When neither of those are an option, we keep going down the line. And this is really where a lot of expertise comes in. Add freeze piles, where you want to keep the ground, frozen. Or are you looking at shallow options like pads and posts, on-grade slabs over insulated embankments? Recently, experience has shown that insulated granular pads just aren't working anymore. Like the sort of to step back for a second, the old design MO was to build a pad of sufficient thickness with non-frost susceptible soil, so you don't get frost-related movements, right? But non-frost susceptible soils, so you actually get aggregation of your permafrost up into that pad, and you don't cause any thaw below and see that reflected in your structure. Even with insulation, there's not really an economical thickness anymore that can be reliably designed. And like, if you're up in alert, you're probably okay, but when you're further south, it's not necessarily true anymore. So you're almost certainly looking at thermal siphon foundations. And if you're getting to that point, that's where you really need to engage experts. So it might be a little selfish here, but another shout out to a Manitoba company just west of Winnipeg, Geotechnical Foundations, great group of people. So to my knowledge, they're the only manufacturers of thermal siphon systems in Canada. So that's who you'd be talking to. Really briefly touch on climate change. This is a good, sorry, keep track of time here. This is a good starting point for assessing climate change effects on your foundations, or the document says infrastructure on permafrost, so it's not necessarily just foundations. But once you know what your project is, you establish your climate zone, E1 through W3 or up to E4. And then pull up whatever charts you want to base your climate change scenario on. So your RCP, represented carbon concentration pathway 4.5, which is your moderate, or 8.5, which is your extreme. So you choose which scenario. That's probably a conversation you want to have with your client based on their risk tolerance. You determine the service life of your structure, and bingo, you have an increase in air temperature, right? That's not ground temperature, that's air temperature. You can conservatively use that as a proxy, but if it's critical to your design, you're doing something a lot more nuanced with numerical modeling and making sure that you have, temperature, like a weather station on site, so you can get good data. All right, so there's I guess introduction to permafrost, kind of a long introduction, but we'll get into some case studies now. Foundations. So foundations on permafrost. This is a project up in northern Manitoba where we have discontinuous permafrost. So really important that we assess where it is spatially, so across the site and down. We used conventional drilling rigs with SPTs. A consultant before us had used some chilled fluid. We suspected that their fluid wasn't actually that chilled, so kind of gave some interesting results. But yeah, just showing here's some samples that we ended up coring through, some ice-rich samples. This is installation of helical piles. Sorry, back up a little bit again here. The infrastructure had very little tolerance for movement, so we had to establish where our ice-rich zones were, or thaw-unstable zones were, and where a suitable bearing layer was. Bedrock was over 100 meters deep, so we weren't getting piles down there. So do we have a thaw-stable zone, within striking range of, conventionally available equipment. Um, so we established that. It turns out it was about 80 feet. Um, Big issue was how do we get through that permafrost? We ended up using helical piles. So this is a tool contractor came up with. They called it the polar penetrator. Basically just a rotating air hammer that would get us down to about 70, 75 feet. Keep the hole open and drive the pile down. Ended up doing a fair number of load tests on this just because, the critical nature of the infrastructure. We want a really good handle on what our pile capacity was. And, the real takeaway from this project was we weren't designing for permafrost. We were designing for thaw, right? So when this permafrost thaws, likely, it's warm permafrost within the life cycle of the structure. Can these foundations handle downdrake? Shallow bedrock, often a condition you'll see in the Arctic. Um, at first glance, it might seem like a relatively easy investigation, but what really complicates things is the remoteness of the sites, right? Often you're just in the middle of nowhere. So again, this is sort of Eastern Arctic. You can see on the maps superficial bedrock at most of the sites, but then you get these thin little veneers of, which could be marine deposited soils, so potentially high salinity. If we have infrastructure that's spotted on these locations, is it possible to move it over somewhere that is massive, massive rock? It's really the rock mass that drove this design. Because if we have say ice-filled joints or a little bit of movement, can we find a rock mass that's large enough to socket into with grouted steel anchors? Basically, it's just a picture of one of the core holes. Permafrost degradation. So that's certainly an issue in a lot of communities. Talking to some folks that we work with a lot, there's a lot of retrofitting going on right now with grade supported structures. Getting thermosiphons installed around them. So this is a site up in Central Arctic again, where they're the same one from the sump video earlier, where they're seeing I don't know, upwards of 300,000 liters per day flow into their sump pit. The client asked that we, try to do an investigation with a backhoe just to see if it would work, save some costs. Like we suspected, it didn't quite work. So we went and implemented a full-on investigation with thermistors and put in some groundwater wells. What was a little confusing or I guess not confusing, but the question that we needed to answer is permafrost is an aquitard, right? Water doesn't flow through frozen ground. So how is this building on a raised granular pad seeing so much inflow into its sump pit? We suspected maybe there was a bedrock channel that you could see in some geological maps that was going to this facility. Maybe that had thawed over time and water was, coming right through, or we weren't quite sure. So we installed these thermistors, and what it actually showed is permafrost had aggregated up into the pad. And it was the temperature profiles were really consistent with the background thermistors we installed. So just a little bit of a guidance, I guess, if when you're doing jobs like this, you obviously want to install thermistors, near the infrastructure, the thing that's maybe changed the thermal regime, and some background ones to see, is everything the same, or are they different? And here we found they're actually pretty the same. So there wasn't any degradation. So okay, is it coming from inside the building? So we did some testing for chlorinity to see if or chlorides to see if there's any or it's municipal source of water. It wasn't. So we started looking at the building practices. You can see here, this is a cross section, the raised pad on the tundra with the sump pit kind of right in the middle. And where's my pen? Laser pointer, here we go. They were discharging the sump right near the edge of the building, like literally a couple feet away from the building. So we thought, like, what if we just extend your sump pipe like 100 feet? What would happen? Lo and behold, here's a chart where you can see, July 25th, so almost 400,000 liters per day going into these sump pits. um, down to, a couple days later, like 9,000. So that was certainly what was happening is they were just recirculating the water. Um, and key takeaways here are in permafrost terrain. Um, it's not always the soil and ice that governs behavior. It's flowing water, and more importantly, good building practices, right? Make sure that your sumps are far away from your building and the water's flowing away. Make sure that your roof leaders are like extended far away. Make sure during construction that you establish good drainage and you maintain it. And not just on your site. You're not building up a site and sending water down to whoever's property, just down the street, and you're causing big issues with them. So the importance of just surface water management in construction permafrost areas is incredibly significant. Another foundation example. So again, sort of central-ish Arctic communications. This one was interesting because not shown that great on this picture, but we did see some pattern ground, so we suspected some ice-rich soils. Um, we did have access to a air track rig, so that was good. Sort of geological background, we're in continuous permafrost, glacial marine sediments and tills, potential for higher levels of salinity. And we suspected that bedrock was going to be somewhere around that 8 to 10 meter mark, right in the maximum possible depth of what we could get for a rock socketed pipe. So we had to tailor our investigation to get recommendations if we needed to go ad freeze, right? There's a lot more risk in ad freeze. They're obviously a little, more expensive. So if you can go rock socketed pipe, you want to go rock socketed pipe. Here's the video that maybe shows a little bit better. Maybe not. Maybe it doesn't show anything. Here we go. Drilling for that site, and you can see how difficult it might be to classify your soils based on how fast those cuttings are coming out of the hole, right? So from that, we were able to produce this information. On the left, you see our ground temperature data. So it's just 3 readings with time. We did have a data logger in place. What experience has showed us is the ground temperatures equilibrate really quickly. Usually within a day or so. Within that upper bit, it took about 3 days, but you can see how consistent those lines are just 3 days after installation with depth. We've got our Tesla log on the right, so we can get our soil type where we have ice. You can see some of the NBNs, and is there any V's in there? I don't see any. And then salinity information at the top. We ended up giving recommendations for both pile types on that one because where the bedrock was, so I'm not sure where it went yet. Last, where ground ice is, really critical to the infrastructure. So mine site, Central Yukon, they're, building a tailing storage facility amongst other things. So we were sub on this job to, a friend we work with up in Whitehorse. Again, it's sear drilling, using chilled brine, continuous core to assess ground ice and permafrost conditions. If you're not doing that at the investigation stage, like you've already lost, you've already misinterpreted your ground conditions. And for infrastructure like this, especially with the recent Eagle Gold failure, it's critical that we properly assess ground ice, site infrastructure in the right location, and make sure that risk of thaw degradation is assessed and removed. Photo inside the drill rig. Here's a picture of some ice-rich core and of the brine solution. So with that being said, we're done. So how do I do? 7 minutes left, Leo. A little longer than I wanted to.